we can increase the speed, increase the force to over 100 micrometer per second, more than 50 body lengths per second. So, like in this case, this published in Angewandte, where we replace the gold with the alloy. This is silver gold alloy. We get tenfold improvement in speed compared to the platinum gold. So now we have replaced the gold with silver gold, 7525, and you'll see in the video tenfold higher speed. This is 10 micrometer per second. This is over 100 micrometer, which is nearly 60 body lengths per second. But it's not only the speed, it's the force, the power to carry cargo, to do many more tasks that you'll see later. And we can control the speed and reactivity by controlling the alloy composition. So you can deposit alloy 25, 50, 75% silver. You see the speed increase. And you can see it even if you do electrochemistry, Tafel plot, you see different alloy composition, the delta E. The speed reflects the delta E of this Tafel plot. So we can tailor the speed and the force. So this was the first challenge. The second challenge, how to navigate, how to guide this motor to their destination in a microchannel, how to control the speed, how to accelerate. So this is extremely important for many, many tasks, speed control and navigation, motion control in general. So we introduce a variety of ways to control the speed by pulsing the temperature, magnetic guidance, electrochemical control of the fuel. All of this allow us to control the motion like this. UCSD, this is a magnetically guided motor, again 2 micrometer wire that are magnetic. They also contain a nickel segment that allow this magnetic guidance, and we can use it for nanofabrication later on for very complex motion patterns. Speed control, so we show that we can regulate the temperature and have a speeding on demand. So this is the room temperature. You have a temperature pulse. You see acceleration from 10 micrometer to 50 micrometer at 50 degrees just by increasing the catalytic activity. And you can see this video. These are 5 pulses of the temperature from room temperature to 50, and you can see the video at room temperature at 10 micrometer, and you step it and they accelerate suddenly, and you can put the brakes and go back, and it's slow instantaneously. So again, if you follow room temperature, 1 pulse, and you step to 50, these are all nanowire, and then you slow it back to room temperature. So it's on-demand acceleration. We also observe that silver can result, the presence of silver can result in sudden acceleration. Actually, we have some leak of silver from reference electron. We saw that in the presence of 10, 20 micromolar of silver, you have acceleration. This is the first example of chemical activation of the motion. And we ask, can we use this acceleration for chemical sensing? If the speed depends on the silver level, we develop this sensor for silver, which is very selective to silver compared to other common ion, and again this semi-log dependence on the silver concentration down to sub-micromolar level. So this was the first example of chemical sensing based on motion, based on speed or distance. And we applied later on to detect DNA, where we use silver nanoparticles. So here we use a silver nanoparticle for detecting DNA. So after the DNA hybridization, we capture the nanoparticle, we add in peroxide and the motor. The peroxide dissolves the silver nanoparticle, leading to accelerated motion. The more DNA, the more silver we have, and the faster is the speed. So we can detect low level of DNA hybridization down to the femtomolar level by this silver-induced acceleration. So you get this type of straight line if you align them, and you see nice calibration plot based on different distance or speed for different target DNA, and you can visualize it directly in the optical microscope. So this led to our work on motion-based biosensing. This example of bacteria, again, different level of bacteria. You can see the different speed from the RNA after lysing the bacteria. So we have all this capability. We have motion control, we have power. Can we use it to carry cargo and deliver and transport it and release the cargo? So the goal is to have the motor pick selectively a cargo, transport it, release it on demand. As you see in this video, picking the cargo, transporting the cargo, then releasing the cargo in the destination and go and pick another one. So again, this was old work, and we show that we can use it now for delivering a drug-loaded particle, which is an important application toward the fantastic voyage. So the future drug delivery system will incorporate propulsion, navigation, cargo towing, all this capability to improve the therapeutic efficiency. So by moving the cargo and have all this mixing and motion, you can accelerate the therapeutic process. And nanomotors are very attractive for delivering the therapeutic payload in very high efficiency and to areas of the body which are currently not accessible. So this is what we want, a vehicle that carries the drug to the destination and autonomously release the drug based on change in the local environment, like a cancer cell, if there's a different pH or protease activity. This will trigger the release of the drug. So this again, we did 5 years ago, work to have liposome loaded with cisplatinum anti-cancer drug. They have iron oxide nanomagnetic particles, so they attach magnetically and we can transport them. You see the nickel, platinum, gold. So these are highly loaded liposome. And the question, what is the maximum load that we can transport? And if you look at Stokes' law, the speed is expected to diminish with the size of the particle. So we are exploring the cargo towing ability. That's why we need more force. For example, here we have a drug-loaded PLGA polymeric particle of 0.7, 1.2, and 2.2 micrometer. So the motor is 2 micrometer, and you see different particle size loaded with drug. And the speed, this is the big particle, and you see the video, slower speed and distance. This is a small one, and you can see here. So we have the big particle, 2.2 average, this is 0.7 micrometer, as you expect from the size dependent of Stokes' law. So we have all this capability of improved speed and power, cargo towing, force, motion control, good lifetime, and this all can be used for manipulating cargo in a microchannel in lab-on-a-chip device. The goal is to have a motor that selectively pick the cargo, navigate in the microchannel, drop the cargo, and do it again and again selectively, like in this animation. So you'll have a receptor, let's say for this cargo. This can be a cancer cell, pick it selectively compared to normal cell, and deliver, and you can follow up with analysis in microchip channel, which are only 2 micrometer diameter. So indeed, we again show that we can navigate the motor in the channel magnetically, in the intersection, very complex channel pattern. Let's see if you see the video. If you can see it, you cannot see, but it's basically you get magnetically we can guide this, or this one, the little one also, again. But this allows us to navigate in the complex microchannel pattern. And then next we can combine this directed motion in the channel with the cargo manipulation. So we'll see that we can pick a cargo and then transport it in the channel network like in the animation. So you guide the cargo through this intersection of a very complex microchannel network. And this is shown here with the motor approaching the cargo, the entrance to the system, and then we'll pick it and navigate it toward a destination like in the animation. So you see pickup of the cargo, transport of this. Now we enter the microchannel here with the cargo, and you can go in this intersection, get the green light with the cargo, like in the animation, and transporting it in the microchannel network. Another important inspiration from nature is this collective behavior. This is like schooling of fish or the swarming of ants or flocking of birds. Can we do the same with synthetic nanomachines? Can they communicate with each other and self-organize to do more complex tasks like act as nanotransporter, drug delivery? So we have a lot of activity on nanorobotic in the UCSD. We are developing very advanced smart robot. The question, can this cooperate with each other, communicate like, again, the birds? So this is the work we showed that we can trigger the assembly of gold nanoparticle by adding hydrazine. You'll see this is a dispersion of the gold particle. When you add hydrazine to the peroxide solution, you form electrolyte gradient that cause this formation of swarm, as you can see in this video. Now we'll spike the hydrazine. In 10 seconds, you'll see small swarm that merge to a larger one, and you form well-defined swarm induced by the hydrazine after 20, 30 seconds. So this is due to this electrolyte gradient mimicking chemical secretion and chemotaxing of animals. Another way to assemble motor is to take this genus particle motor. They have an hemisphere of platinum, and the other part is hydrophobic on a silica surface. You can use hydrophobic interaction to assemble the motor into dimer and trimer, and you can duplex, and I don't think we have the video, but here we have example when we organize the cargo. So this is one of these hydrophobic motor, the platinum push it, and all these are hydrophobic cargo that self-assemble in the optimal way, and we can transport this cargo by using a single motor. So this